Performing live examination on an endpoint means that we're investigating a system while it's actively running. Right? We're looking for various artifacts or indicators of compromise that might reveal a potential intrusion, all in an effort to help us make a determination whether or not a system's compromised. Now, every endpoint runs countless legitimate programs to perform its day-to-day operations or interact with core system components. But it's important to remember that generally, at some point during an active intrusion, malware also needs to run as a process, or at the very least, hide within one. And that makes performing analysis on actively running processes a very fruitful early step during live investigation. Now, in this video, we'll focus specifically on different ways in which we can interrogate processes on a Windows endpoint. But keep in mind that live investigation extends much farther into areas like network traffic or different persistence mechanisms like the Windows registry or scheduled tasks and installed services. Having a strong methodology for enumerating and analyzing these artifact sources together can help paint a much clearer picture of what's going on under the hood on an endpoint, making it that much easier to spot evil. To put it simply, a process is simply a program that's currently executing. Now, each process has its own self-contained environment providing the different resources needed for an application to run, including things like its own virtual address space, the code, right? All of the open system object handles. Now, attackers can abuse processes for their own benefit in many different ways. For example, they can launch their own malware as a standalone process. They can inject malicious code or migrate into legitimate processes to stay under the radar. Or they can manipulate a system process to escalate their privileges or their security context on the endpoint. Ultimately, every stage of an intrusion, whether it's the initial access, execution, persistence, or defense evasion, all of these different steps can leave behind process-related evidence. And by examining running processes on a system, or the different parent-child relationships, or command line arguments, things like loaded modules and execution context, incident responders can really reconstruct an attacker's actions and identify anomalies that deviate from normal behavior. Our first step in analyzing processes is to be able to effectively enumerate the active running processes on a system. Now, oftentimes, organizations will have third-party tools like an EDR or XDR or different managed detection and response platforms to help provide system context. Now, these are fantastic resources for performing live investigations, but keep in mind that these tools aren't always readily available in all organizations, and they can also sort of abstract away some important details. And that abstraction can sometimes lead to more inexperienced analysts jumping to conclusions about the data that it's collecting and presenting. Now, you might be familiar with some of the legacy command line tools that are used to enumerate process information on a Windows system. For example, the task list executable, right? Tasklist.exe can be used to quickly display a list of the currently running processes on either a local or remote computer. And as a note here, when we're interrogating things like processes or services or network connections on a Windows system, we want to be doing so under an administrator context, similar to how we'd want to perform this as the root user on a Linux operating system. And so just keep that in mind. We want to be in an administrator command prompt or PowerShell session. And so just running task list by itself here is going to output all of the active processes, showing things like their names, right? Image name or the process ID or the PID number, things like the session name and the session number, along with the memory usage as well, just giving us a nice quick baseline of what's running on the system. Now, we can even filter for specific process IDs or process names using the filter argument. And so, for example, if I filter here where the process ID or the PID number equals 664, in this case, I'm going to pull back the CSRSS or the client server runtime subsystem service executable. Alternatively, I can filter based off of an image name as well. And so I just have an empty notepad process running here. And so if I filter based on the image name of notepad.exe, well, we should be able to pull back, in this case, the process ID of 11848, which refers to my notepad process. If I were to kill this process just by exiting out of notepad and run this again, well, now we don't have any tasks or processes running with that process ID because it's since been terminated. Another legacy command line utility to query process information and retrieve additional properties like the parent process and command line arguments from running processes is WMIC, or Windows Management Instrumentation command line, which has since been deprecated on modern Windows systems. And so what we used to be able to do is run something like WMIC here and search for a process class where, for example, the process ID equals a specific process ID. And we can grab different properties from WMI, like the name or the process ID, the parent process ID, or the command line arguments as well. Now, when we run this, you see I won't be able to, since it's not installed by default on these newer Windows 11 builds. Although if I were really determined, I could still install it just by going here to turn Windows features on or off, and I can go down and manually enable WMIC if I really wanted to. Now, these legacy methods are still valuable in their own right, and you'll still run into plenty of systems that still have WMIC installed these days. But they do have quite a few limitations, and as we've seen, for the most part are becoming deprecated from the operating system. And so what should we be moving towards now? Well, ultimately, PowerShell is Microsoft's modern task automation and configuration management framework. And if we want to be effective analysts and responders, we need to be comfortable with using PowerShell to query and inspect and manipulate system data, or automate repetitive tasks and gather detailed forensic information from endpoints. And in PowerShell, we have access to the aptly named Get-Process commandlet. Now, Get-Process allows us to quickly and easily list out the running processes on a Windows system. All right, so very similar to how we just ran with task list, but this time we're using PowerShell commandlets. And when we pull back Get-Process on its own, we're going to see several different columns or properties that return to our output listing. And so we can see things like the handles, right? So the different files open or sockets or name pipes or just other resources attached to these individual processes. We can see non-page memory in kilobytes here. We can see the paged memory, right? Or the memory that's been paged to disk or swap. We can see the working set here, or the total combined memory used by the process, right? So considering things like non-page memory, page memory, and even other memory like the executable itself. We can see CPUs here, right? So the amount of CPU time used by the process. We can see the process IDs here with the ID property, right? And so each process has its own unique process ID or PID number. And these PIDs can change from system to system because they're kind of assigned sequentially by the operating system. And they also roll over. And so you might see some smaller numbers as things were executed, closer to the startup of the operating system, and also larger numbers, right? And sometimes you'll even see process IDs get reused over time as processes start and terminate. We also have the session identifier indicating the different logged in users, and the process name as well, telling us what exactly the name of each process is. Now, of course, we can filter the output of the Get-Process commandlet as well. And as best practice, when we work with PowerShell, we want to adhere to this concept of filter left. Now, filter left is the principle of filtering as early as possible in our command pipeline. And so if you've ever worked with a SIEM or a SIM system before, like Splunk or Elastic or Microsoft Sentinel, you're probably familiar with this concept, right? The idea is we want to reduce the overhead on our different processes or our search head by filtering as early as possible to limit the amount of results that we're returning. And so if we wanted to filter for, say, different notepad processes, it would be less effective to run a query like this, where we're grabbing all the different processes, right? So we're first grabbing all the running processes, then using the pipeline, we're evaluating the where object clause for each of those processes where the process name equals notepad. Now, what I need to do here to actually return something is open up another notepad window here. If I run this, we should get a result here, right? Now, this came back very quickly, but you can imagine if we're querying hundreds of different processes on a system, or thousands of processes across multiple systems, well, it's not the most effective way from a resource perspective to get this information. Now, fortunately, like many different commandlets here to interrogate different system processes, Get-Process gives us the built-in name parameter here. And by doing it this way, we are filtering as far to the left as possible, right? In fact, we aren't even piping anything to where object in this case. And if I run this, we're going to get the exact same information. And in fact, because the name parameter is actually positional in nature, we don't even need to include that parameter when we specify the name of the process we're trying to return. In fact, we can actually use wildcards with Get-Process as well, right? So if I just search for note with an asterisk here as a wildcard, we're still going to pull back the same process. Now we could do the same thing with the process ID as well, right? So we can see here that the process ID for Notepad, in my case, is 10520. And so if I run get process with the ID parameter of 10520, again, we're going to pull back the exact same result here. And because with PowerShell, we're returning our results as an object, well, we get access to all the powerful pipeline of capabilities that PowerShell offers that allows us to filter and extract different properties from each of the running processes that we're returning. All right, so in this case, what I can do here is run the same command again, this time piping it over to select object to specifically grab the process name, ID, the path of the binary, and a description as well. And so just like that, we're now pulling back not only the name and the process ID, but also the path of where this binary is executing on the system, along with its description, which in reality is just giving us the full binary name with the file extension. But you'll notice that we can't actually see that column here. Sometimes these columns or properties can get cut off and truncated. Now to avoid that, sometimes I like to finish off my command here with a final format -list. And this is going to display each property on a single line. And so you can see by doing that, we now sort of avoid that issue, and we're now getting the description field here, indicating we have notepad.exe running, along with the full path to that binary as well. We can also zoom back out on the endpoint and hunt for different anomalies across the entirety of our process list. Right, for example, the path property allows us to see the full path of the executable. What if we wanted to filter out any processes that are currently executing out of the system32 directory, or out of any of the program files directories? Well, to do that, we can run a semi-complicated PowerShell query here, basically to grab all the processes where the path exists, but the path is not located in system32 or any of its subdirectories, or in C:/program files or C:/program files x86 for those 32-bit binaries. And then we're just piping that over to select object to grab the name, ID, and the path. And by doing that, we were really able to cut down on a lot of the noise. And out of this subset, although some of our columns here are being truncated, we can identify that we have an interesting process in the mix here. You can see that we have this lsas.exe process running out of a user's downloads directory, which is definitely not normal. And also, this isn't a silver bullet, but I notice that the process ID here is a little bit high for LSAS being a core system process, which is usually a bit lower in the list as many of these core system processes are launched on system startup. And so I definitely want to zoom into this process and investigate it farther. And so what I'm going to do here is just set this process over to a variable so I can reference it later. We don't have to do this, but as best practice, I just like to sort of work in this way when I'm in a PowerShell session. And so I'm just going to save this suspicious process ID here over to 4856. Now we can get a ton of useful information by selecting different get process properties. In fact, we can list them all by piping get process over to the get member commandlet, essentially to identify all the different members or properties and methods of these objects. And so as we go through this list of properties, you'll notice that we have a ton that we can grab, right? At the very top here, we're going to see different methods, right? So we can kill processes, we can refresh or start processes. But if we focus on properties here, again, you can see we can grab things like the ID, we can grab things like non-page memory size, the priority class, or things like the path and file version and description. But you'll notice that there isn't really anything for retrieving a parent process ID, or to list out the command line invocations or arguments for a process. Now for that information, we need to turn to a secondary commandlet that can actually query WMI classes. And the modern way to do that in PowerShell is with Get-CimInstance. By the way, if you do enjoy this kind of thing, we recently released the Security Operations 201 course on the TCM Academy, which dives much deeper into incident response and threat hunting and investigating intrusions at scale. We get much deeper into using PowerShell for incident response investigations, as well as powerful artifact collection methodologies. And so feel free to check it out. I think you'll really enjoy it. CIM stands for the Common Information Model, which is this standardized way to represent and organize information about systems or devices and applications. It sort of defines this common schema of different classes and properties and relationships between those so that different management tools and platforms can query and interact with this system data. Now, to retrieve the command line and parent process ID of a process, we can run Get-CimInstance or Get-CimInstance against the win32_process class. Specifically, we can even filter based off of a process ID. And so what I'm doing here is passing in the process ID of that suspicious PID variable that I set earlier. And then I'm just piping that over to select object to grab the name, the process ID, so it gets cut off here, but the command line property, as well as the parent process ID as well. And then I'm just going to format that as a list once more. And so by doing that, we can see a lot of the same information that we were just looking at with getProcess. But we can now see the command line invocation of that process as well. Now in this case, it doesn't appear that there were any additional command line arguments passed to the process, and so we're just seeing the same path that was executing out of the downloads directory, which is still suspicious, but not super telling or not additional information that we didn't already have. But another property we get access to with Get-CimInstance is the parent process ID, which in this case we can see is set to 6188. And by grabbing this parent process ID, we can work our way up the execution tree and figure out what the parent process was for this suspicious process. And so what I can do here is run Get-CimInstance again, this time filtering for the process ID of 6188 that we've identified is the parent process of this suspicious LSAS executable. And when we do that, we can see that it was invoked by explorer.exe. And this is often the case if a process was executed from, say, a user's desktop, or say from the Explorer window, or from the Start menu as well. Now what we can also do from here is go in the other direction, right? So we can see what child processes were spawned from lsas.exe. And so what I'll do here is pipe Get-CimInstance over to where_object so I can list out any child processes of this 4856 LSAS process. And when I do that, we can see two processes are listed. So first here we have conhost.exe or container host. Now this is kind of like a shell process and is often a precursor to launching a command prompt or a PowerShell session, which we can see here as a sibling process as well. And so we have PowerShell.exe. Now this PowerShell process seems a bit more enticing here, and so I want to know what command line arguments might have been passed over to it. All right, we have a suspicious executable seemingly masquerading as the legitimate lsas.exe process, or the local security authority subsystem service, which is quite a frequent target for attackers trying to dump credentials, for example. And so seeing it spawn a PowerShell process is a little suspicious here. And so I want to see what command line arguments might have been passed over to this PowerShell process. And so what I'm going to do here is run Get-CimInstance against the win32 process class, filter for the process ID of 10256, or that PowerShell process ID. And then I'm going to grab the name, the process ID, the command line, and the parent process ID as well, and format that as a list. And just like that, we return the full process with its command line property, which is kind of the elephant in the room here that we can't ignore, right? This is looking quite suspicious right out of the gate here. Even if we didn't know what was going on here exactly, seeing this long string of encoded PowerShell like this should immediately get us concerned. Now what I can do here is grab just this long string of base64 text and paste it into something like CyberChef so we can quickly decode its contents. And the reason why you can recognize that this is base64, well, first off, we're passing the E argument here, or the encoded command parameter over to PowerShell, which is used to pass in a base64 encoded string. But we can also see that we have two equal signs at the end here, which is pretty common for base64 strings as padding characters. And also based on the character set as well, right? We have these printable ASCII characters here. We have the upper and lowercase alphabet along with numbers 0 through 9. And so over in CyberChef, I'm going to paste in this long string of base64, and I could clean it up if I really wanted to, but it shouldn't really make a difference here. I'm going to drag in the from base64 operation here into my recipe. We're going to notice we're getting pretty close. We have these null characters here. And so what we have to do is decode this from UTF-16LE. And so when you run PowerShell with the encoded command, or that E flag that we saw, PowerShell doesn't use the standard UTF-8. Instead, it encodes the command using UTF-16 little endian, or LE, before base64 encoding it. And so what I can do here is go up to Operations, search for decode text, and drag that now into my recipe, and change the encoding here to UTF-16LE. We've now decoded the script that was passed into that PowerShell process. And what this appears to be doing is opening up a TCP connection over to 10.0.2.15 over port 443. And it's reading in data from the remote side and executing that data in PowerShell. And so this is a very common reverse shell script that we commonly see encoded into base 64 and run from the command line. And so just like that, we were able to use a few simple but effective PowerShell commands here to really walk through the process information on this running system and use a few different filtering techniques to really hone in and find evil. And no matter what we're hunting, if we're looking at processes, we can use the get process commandlet and things like Get-CimInstance to really help us out during investigations, not only from a local system like we're doing here, but also remotely and at scale using PowerShell remoting. There's a reason why Microsoft really wants us to use PowerShell, because it's just full of functionality and power once we know how to use it effectively for incident response investigations. Now, that was quite the deep dive into investigating processes, and this feels like a natural stopping point for now. But there's still so many attributes and evidence sources on a Windows system, particularly around process activity, that can help us identify indicators of compromise or other artifacts that can help us piece together an attack timeline. But ultimately, as a takeaway here, when analyzing processes, use what you can from your own internal threat intelligence to help determine if a process is new to the environment, or unrecognized, or maybe it has a suspicious or a random name, right? Verify things like its execution path, right? As we talked about, legitimate processes usually run from folders like System32 or program files. But even then, we can't just blindly trust that because something's running out of System32 that it's legitimate. There's always so much nuance here. But fortunately, we have other indicators as well, right? We can examine the parent process for normal relationships, right? For example, if we see WinWord spawning cmd.exe or PowerShell, that's probably not a good sign. And watch out for suspicious behavior, like seeing highly obfuscated or complex command line arguments passed into a process. Now, these are sometimes used legitimately, but very often an indicator of malicious activity. Now, these kind of recommendations aren't exhaustive, right? But they can help you identify anomalies much faster. For example, the Hunt Evil poster from the SANS Institute does a great job at cataloging many core system processes and baselining what is the normal or expected activity from them. Either way, we'll always need to perform additional analysis to truly determine if a process is malicious. And once we understand what normal looks like in our environment, we can use visual cues and differential analysis to help us identify anomalies almost immediately. Now, in the next installment of this live investigation series, we'll shift our focus over to network analysis and how we can start correlating what we're seeing on the network over to endpoint processes, or look into how we can enumerate listening ports or active TCP sessions. And so thank you for watching, and feel free to leave a like if you want to see more of this content, and subscribe if you haven't already. Take care.